Hello everyone, welcome back. I'm your friend in XO. Today we will try to get into the section Polynomial Division.
Polynomial division.
We're already familiar with the idea of a polynomial, and we've spent some time adding polynomials, subtracting polynomials, and multiplying polynomials, and factoring polynomials. And what we're going to think about in this video, and really start to think about in this video, is the idea of polynomial division. So, for example, if I had the polynomial, and this would be a quadratic polynomial, let's say x squared plus 3x plus 2, and I wanted to divide it by x plus 1. Pause this video and think about what would that be? What would I have to multiply x plus 1 by to get x squared plus 3x plus 2? Well, one way to approach it is we could try to factor x squared plus 3x plus 2, and we've done that multiple times in our lives. We think about, well, what two numbers add up to 3? And if I were to multiply them, I get 2, and the one that might jump, or the ones that might jump out at you are 2 and 1. And so we could express x squared plus 3x plus 2 as x plus 2 times x plus 1, and then all of that is going to...
Okay, pause in here and let me think about it. Why this stuff would be ended up in this form? For now, what you know is that we got a number of 2 and we got a number of 1. Where the two numbers was coming from? How he know that the two number was the right number for this form change? Well, you could know something. For example, the 2 plus the 1 is 3, and 2 times the 1 equal to 2. That's how he made that decision that he's gonna use the 2 and 1 to compose this expression.
To be over x plus 1. And so if you were to take x plus 2 times x plus 1 and then divide that by x plus 1, what is that going to be? Well, you're just going to be left with an x plus 2. This is going, I don't have to put parentheses. This is going to be an x plus 2. And if we want to be really mathematically precise, we would say, hey, this would be true as long as x does not equal negative 1, because if x equals negative 1 in this expression or in this expression, we're going to be dividing by 0, and we know that leads to all sorts of mathematical problems. But as we see, for any other x, as long as we're not dividing by 0 here, this expression is going to be the same thing as x plus 2, and that's because x plus 2 times x plus 1 is equal to what we have in this numerator here. Now, as we go deeper into polynomial division, we're going to approach things that aren't as easy to do just purely through factoring. And that's where we're going to have a technique called polynomial long division. Polynomial long division, sometimes known as algebraic long division. And if it sounds familiar because you first learned about long division in 4th or 5th grade, it's because it's a very similar process where you would take your x plus 1 and you would try to divide it into your x squared plus 3x plus 2. And you do something and I'm going to do a very quick example right over here, but we're going to do much more detailed examples in future videos. But you look at the highest degree terms. You say, okay, I have a first degree term and a second degree term here. How many times does x go into x squared? Well, it goes x times. So you put the x in the first degree column, and then you multiply your x times x plus 1. X times x is x squared. X times 1 is x. And then you subtract this from that. So you might already start to see some parallels with the long division that you first learned in school many years ago. So when you do that, these cancel out. 3x minus x, we are left with a 2x, and then you bring down that 2. So 2x plus 2. And you say, how many times does x go into 2x? Well, it goes 2 times. So you have a plus 2 here. 2 times x plus 1. 2 times x is 2x. 2 times 1 is 2. You can subtract these, and then you are going to be left with nothing. 2 minus 2 is 0. 2x minus 2x is 0. So in this situation, it divided cleanly into it, and we got x plus 2, which is exactly what we had over there. Now, an interesting scenario that we're also going to approach in the next few videos is, what if things don't divide cleanly? For example, if I were to add 1 to x squared plus 3x plus 2, I would get x squared plus 3x plus 3. And if I were to try to divide that by x plus 1, well, it's not going to divide cleanly anymore. You could do it either approach. One way to think about it, if we know we can factor x squared plus 3x plus 2, is say, hey, this is the same thing as x squared plus 3x plus 2 plus 1, and then all of that's going to be over x plus 1. And then you could say, hey, this is the same thing as x squared plus 3x plus 2 over x plus 1 over x plus 1 plus 1 over x plus 1 plus 1 over x plus 1. And we already figured out that this expression on the left, as long as x does not equal negative 1, this is going to be equal to x plus 2. So this is going to be equal to x plus 2, but then we have that 1 that we weren't able to divide x plus 1 into, so we're just left with a 1 over x plus 1. And we'll study that in a lot more detail in other videos. What does this remainder mean? And how do we calculate it if we can't factor part of what we have in the numerator? And as we do our polynomial long division, we'll see that the remainder will show up at the end when we are done dividing. We'll see those examples in future videos.
Yeah, so the operation that we were been doing is called division, and the division, this concept, we have learned it a long time ago, back to the let's say primary school, I guess. But for this time, we were doing it differently. We were doing it with polynomial.
Simplify the expression 18x to the fourth minus 3x squared plus 6x minus 4, all of that over 6x. So there's a couple of ways to think about them. They're all really equivalent. You can really just view this up here as
So for each of the time, for every morning, what I did is watch the videos and never think about why he wanna do that. Or I may think, but I never tried it before he do that kind of explanation. So for this time, I'm gonna do it differently. I'm going to try to solve it by myself. Then I'll watch the video. Okay, for this time, let's say we got 18x to 18x to the fourth power minus 3x squared plus 6x minus 4 over the 6x. For this one, how can we simplify it? That was kind of interesting because I generally do not know how to simplify it, but I guess I make something like, 3x to the fourth power minus 1 over 2x squared plus x minus 2 over 3, and in the end I'll just leave the x in the denominator. That's the best that I could do, but the Cohen must have a better solution than us, so let me get into it.
being the exact same thing as 18x to the fourth over 6x plus negative 3x squared over 6x, or you could say minus 3x squared over 6x plus 6x over 6x minus 4 over 6x. Now, there's a couple of ways to think about it. One is I just kind of decompose this numerator up here. If I just had a bunch of stuff, a plus b plus c over d, that's clearly equal to a over d plus b over d plus c over d. Or maybe not so clearly, but hopefully that helps clarify. Another way to think about it is kind of like you're distributing the division. If I divide a whole expression by something, that's equivalent to dividing each of the terms by that something. The other way to think about it is that we're multiplying this entire expression. So this is the same thing as 1 over 6x times this entire thing, times 18x to the fourth minus 3x squared plus 6x minus 4. And so here, this would just be the straight distributive property to get to this. Whatever seems to make sense for you, they're all equivalent. They're all logical, good things to do to simplify this thing. Now, once you have it here, now we just have a bunch of monomials that we're just dividing by 6x. And here we can just use exponent properties. This first one over here, we can take the coefficients and divide them. 18 divided by 6 is 3. And then you have x to the fourth divided by x to the, well, they don't tell us, but if it's just an x, that's the same thing as x to the first power. So it's x to the fourth divided by x to the first. That's going to be x to the 4 minus 1 power, or x to the third power. Then we have this coefficient over here, or these coefficients. We have negative 3 divided by 6. So I'm going to do this part next. Negative 3 divided by 6 is negative 1/2. Negative 1/2. And then you have x squared divided by x. We already know that x is the same thing as x to the first. So that's going to be x to the 2 minus 1 power, which is just 1. Or I could just leave it as an x right there. Then we have these coefficients. 6 divided by 6, well, that's just 1. So I could just, well, I'll write it. I could write a 1 here. Let me just write the 1 here, because we said 2 minus 1 is 1. And then x divided by x is x to the first over x to the first. You could view it two ways. Anything divided by anything is just 1, or you could view it as x to the 1 divided by x to the 1 is going to be x to the 1 minus 1, which is x to the 0, which is also equal to 1. Either way, you knew how to do this before you even learned that exponent property, because x divided by x is 1. And then assuming x does not equal 0. And then finally, and we kind of have to assume x doesn't equal 0 in this whole thing, otherwise we would be dividing by 0. And then finally, we have 4 over 6x. And there's a couple of ways to think about it. So the simplest way is both negative 4, let me do it, negative 4 over 6 is the same thing as negative 2/3. Just simplify that fraction. And we're multiplying that times 1 over x. And so we could multiply that times 1 over x. So we could view this 4 times 1 over x. Another way to think about it is you could have viewed this 4 4 is being multiplied by x to the 0 power, and this being x to the first power. And then when you tried to simplify it using your exponent properties, you would have, well, that would be x to the 0 minus 1 power, which is x to the negative 1 power. So we could have written an x to the negative 1 here, but x to the negative 1 is the exact same thing as 1 over x. And so let's just write our answer completely simplified. So it's going to be 3x to the third minus 1/2 x plus 1, because this thing right here is just 1. So plus 1, and then minus 2 times 1 in the numerator over 3 times x in the denominator. And we are done. Or we
So let's say according to this video, I'm pretty sure what I did here is not the best solution, or it's not the end solution. It's a solution, but not the best. So so we need to do a further simplification. In this case, as we could split the numerator apart. For example, now that will be something like this: 3x to the fourth power over x minus 1/2 x to the 2 power, or x squared, over the x plus the x over x, and then minus 2 over 3 then over x, something like that. Then we're gonna go further. For example, we would get 3x to the third power minus 2x plus 1 minus 3 over 2 x to the negative 1 power. And in other words, that would be, let me do it again. This one, that would be something like this: minus 2x3. Alright, I don't know if this was right. Let me just do a verification. Come on, we got an error. That makes sense. We'll probably get the right answer by doing it from the very beginning. They call it divide distribution, right? Are we gonna make it? So for now, that seems to be correct. And for this one, if we do it carefully, we would end up something like this. Okay, this is tricky. I don't know if you have noticed this item here. That'll be equal to 1x times. Okay, divide something is another word. In another words, that will be times the 1 over that something. Yeah, for this case, that will be 1/2 x. Okay, that's probably the final answer for the simplification problem: dividing quadratics by linear factor.
In this video, we're going to learn to divide polynomials. And sometimes this is called algebraic long division. But you'll see what I'm talking about when we do a few examples. So let's say I just want to divide 2x plus 4 and divide it by 2. And we're not really changing the value. We're just changing how we're going to express the value. So we already know how to simplify this. We've done this in the past. We could divide the numerator and the denominator by 2. And this would be equal to what? This would be equal to x plus 2. Let me write it this way. It would be equal to, if you divide this by 2, it becomes an x. You divide the 4 by 2, it becomes a 2. If you divide the 2 by 2, you get a 1. So this is equal to x plus 2, which is pretty straightforward, I think. The other way is you could have factored a 2 out of here, and then those would have canceled out. But I'll also show you how to do it using algebraic long division, which is a bit of overkill for this problem. But I just want to show you that it's not fundamentally anything new. It's just a different way of doing things. But it's useful for more complicated problems. So you could have also written this as 2 goes into 2x plus 4 how many times? And you would perform this the same way you would do traditional long division. You'd say 2, you'd always start with the highest degree term. 2 goes into the highest degree term. You would ignore the 4. 2 goes into 2x how many times? Well, it goes into 2x x times. And you put the x in the x place. X times 2 is 2x. And just like traditional long division, you now subtract. So 2x plus 4 minus 2x is what? It's 4, right? And then 2 goes into 4 how many times? Goes into 2 times. Positive 2 times. Put that in the constants place. 2 times 2 is 4. You subtract, remainder 0. So this might seem overkill for what was probably a problem that you already knew how to do and do it in a few steps. But we're now going to see that this is a very generalizable process. You can do this really for any degree polynomial dividing into any other degree polynomial. Let me show you what I'm talking about. So let's say we wanted to divide x plus 1 into x squared plus 3x plus 6. So what do we do here? So you look.
That was quite interesting. So I'll try to solve it by myself first. So you got a division. For now, that will be x plus 1. It's going to be the divisor. X squared plus 3x plus 6. This is going to be divided by x plus 1. how can we do this division? Let's say at the first, I'm going to multiply the x plus 1 by x. So if we do that, what we would get? We would get x squared plus 3x. Was that correct? No, it's not correct. There should be just the x. Okay, for now the x squared was cancelled out. 3x minus x would be equal to 2x. Then we left with 6 here. Again, we're gonna try to compose an expression just like this one. So how can we do that? So we're gonna plus 2. If we times the 2 with the x plus 1, what we would get? We would get 2x plus 2. For this case, the 2x was cancelled out. The 6 minus 2 would be 4. Alright, for now we got a 4 left in there. But to be honest, I don't know how to make it disappear. So I'll just get back to the video and see how would he handle it.
Look at the highest degree term here, which is an x, and you look at the highest degree term here, which is an x squared. So you can ignore everything else, and that really simplifies the process. And you say x goes into x squared how many times? Well, x squared divided by x is just x, right? X goes into x squared x times, and you put it in the x place. This is the x place right here, or the x to the first power place. So x times x plus 1 is what? X times x is x squared. X times 1 is x. So it's x squared plus x. And just like we did over here, we now subtract. And what do we get? X squared plus 3x plus 6 minus x squared. Let me be very careful. This is minus x squared plus x. Don't want to make sure that negative sign only, it applies to this whole thing. So x squared minus x squared, those cancel out. 3x, this is going to be a minus x. Let me put that sign there. This is minus x squared minus x. Just to be clear, we're subtracting the whole thing. 3x minus x is 2x. And then you bring down the 6, or 6 minus 0 is nothing. So 2x plus 6. Now you look at the highest degree term, an x and a 2x. How many times does x go into 2x? What goes into it 2 times? 2 times x is 2x. 2 times 1, 2 times 1 is 2. 2 times 1 is 2. So we get 2 times x plus 1 is 2x plus 2. But we're going to want to subtract this from this up here. So we're going to subtract it. Instead of writing 2x plus 2, we could just write negative 2x minus 2 and then add them. These guys cancel out. 6 minus 2 is 4. And how many times does x go into 4? Well, we could just say that 0 times, or we could say that 4 is the remainder. 4 is the remainder. So if we were to rewrite, if we wanted to rewrite x squared plus 3x plus 6 over x plus 1, notice this is the same thing as x squared plus 3x plus 6 divided by x plus 1. This thing divided by this. We can now say that this is equal to x plus 2. It is equal to x plus 2 plus the remainder divided by x plus 1 plus 4 over x plus 1. This right here and this right here are equivalent. And if you
Alright, so for somehow he's a genius that come up with an idea. He somehow will generalize the rule for doing that long division. In this case, we could just use that formula to get the result of x squared plus 3x plus 6 over x plus 1. We could get the result by doing this process. And in the end, what we got is x plus 2. Then for this one, this is the remainder. So for that one, that will be 4 over x plus 1. So I must say this is quite new to me. I didn't know this method before, so that's probably why I always couldn't solve complex division, polynomial division before, because I don't know how to do it, right? Then how can I make it right? Especially in the exam, I didn't know that, right?
If you wanted to check that, if you wanted to go from this back to that, what you could do is multiply this by, you could multiply it by x plus 1 over x plus 1 and then add the 2. So this is the same thing as x plus 2. And I'm just going to multiply that times x plus 1 over x plus 1, right? That's just multiplying it by 1. And then to that, add 4 over x plus 1. I did that so I have the same common denominator. And when you perform this addition right here, when you multiply these two binomials and then add the 4 up here, you should get x squared plus 3x plus 6. Let's do another one of these. They're kind of fun. So let's say that we want to simplify x squared plus 5x plus 4 over x plus 4. So once again, we can do our algebraic long division. We can divide x plus 4.
Again, for this kind of problem, let me just do it by ourselves before we see the solution. So we're gonna divide x squared plus 5x plus 4. We're gonna divide it by x plus 4. How can we do that? First, we're gonna multiply it by x. In this case, we would get x squared plus 4x. Of course, we're gonna minus it to the original expression. In this case, the x squared was cancelled out. 5x minus 4x would be 1x, and we're left with a 4. And for now, what we need to do is to multiply the x plus 1 by 1. Then we would get x plus 4. And for now, everything was cancelled out. We got the 0 right in there. So we could rewrite the whole stuff into, or we could say the result for the original division would be just equal to x plus 1. That was simple. I didn't know that before, but it will definitely be useful because I think the Chinese exam, especially the mathematics exam, are they are very likely to ask you a question of a very complex polynomial, which have a, let's say, have a numerator and a denominator, something like that. That's a general form for the exam, for the mathematics exam. Let's jump into the last video, or the quadratics.
This polynomial division business is a little bit more fun than we expected, so let's keep going. So let's say that, I guess again, someone walks up to you in the street and says, what is x squared plus 1 divided by x plus 2? So pause this video and have a go at that, and I'll give you...
Alright, new mission just arrived. We need to calculate out the x squared plus 1 over x plus 2. Can we get the result back? Well, we could, and let me try it out. X squared plus 1 divided by x plus 2. Well, at the first I will try to multiply it by x. In this case, we would get x squared plus x. What the fuck? Now, even if we cancel out the x squared, we would left with the, let's say, 1 minus x. So in the end, we would get an answer like x plus 1 minus x divided by x plus 2. I don't know if this was the right answer, so I'm gonna check the video.
Give you a little bit of a warning. This one's a little bit more involved than you might expect. All right, so there's two ways to approach this. Either we can try to re-express the numerator where it involves an x plus 2 somehow, or we could try to do algebraic long division. So let me do the first way. So x squared plus 1, it's not obvious that you can factor it out, but can you write something that has x plus 2 as a factor, and interestingly enough has no first degree terms, because we don't want some weird first degree terms sitting up there. And the best thing that I could think of is constructing a difference of squares using x plus 2. So we know that x plus 2 times x minus 2 is equal to x squared minus 4. So what if we were to write x squared minus 4 up here, and then we would just have to add 5 to get to plus 1. So what if we were to write x squared minus 4, and then we write plus 5? This expression and that expression up there, those are completely equivalent. But why did I do that? Well, now I can write x squared minus 4 as x plus 2 times x minus 2. And so then I could rewrite this entire expression as x plus 2 times x minus 2, all of that over x plus 2, plus 5 over x plus 2. And now, as long as x does not equal negative 2, then we could divide the numerator and the denominator by x plus 2. And then we would be left with x minus 2 plus 5 over x plus 2. And I'll put that little constraint if I want to say that this expression is the same as that first expression for x not equaling negative 2. And so here we'd say, hey, x squared plus 1 divided by x plus 2 is x minus 2. And then we have a remainder of 5. Now let's do the same question, or try to rewrite this using algebraic long division. We'll see that this is actually a little bit more straightforward. So we are going to divide x plus 2 into x squared plus 1. Now, when I write things out, I like to be very careful with my, I guess you could say, my different places for the different degrees. So x squared plus 1 has no first degree term. So I'm going to write the 1 out here. So second degree, no first degree term. And then we have a 1, which is, you can view as our 0th degree term or our constant term. And so we do the same drill. How many times does x go into x squared? We're just look at the highest degree terms here. X goes into x squared x times. That's first degree. So I put in the first degree column. X times 2 is 2x. X times x is x squared. And now we want to subtract. And so what is this going to be equal to? We know the x squareds cancel out. And then I'm going to be subtracting negative 2x from, you could view this as plus 0x. x up here, plus 1. And so you're left with negative 2x. And then we bring down that 1 plus 1. X goes into negative 2x, negative 2 times. Put that in the constant column. Negative 2 times 2 is negative 4. And then negative 2 times x is negative 2x. Now we have to be very careful here because we want to subtract the negative 2x minus 4 from the negative 2x plus 1. We could view it as this, or we could just distribute the negative sign, and then this will be positive 2x plus 4, and then the 2x's, the 2x and the negative 2x cancels out. 1 plus 4 is 5, and there's no obvious way.
It seems like I made a mistake at my calculation. So let me see if I can quickly fix it. Again, I put the x into x, so I get x squared plus 2x. This time the x squared cancel out. What we got is 1 minus 2x. And if we think about it again, it's just another, let's say we could rewrite that kind of thing with negative 2x plus 1. Okay, for now I'll just add another 2 to it. So we will get 2x plus 4. And remember, we're gonna minus the whole stuff. So for this case, what we got is 0. If we do that, that would be a big mistake because we would only make the x have a higher coefficient number, so we wouldn't do that. So instead of plus 2, we'll say minus 2. If we do it in that way, we would get negative 2x minus 4, and we add a minus symbol at the beginning of the whole expression. We can rewrite it as something like this, plus 2x plus 4. So in the end, the 2x was cancelled out. We only got the 5 left in there. So in the end, the answer would be x minus 2 plus 5 over x plus 2. Yeah, I think we were right if you look at the answer in that video.
Dividing x plus 2 into 5, so we would call that the remainder, exactly what we had before. When we divided with algebraic,
then let's get into the division with polynomial, right?
We're told divide the polynomials. The form of your answer should either be just a clean polynomial or some polynomial plus some constant over x plus 2 where p of x is a polynomial and k is an integer. Fair enough. And if we were doing this on Khan Academy, this is a screenshot from Khan Academy, we would have to type this in, but we're just going to do it by hand. And
fine. So let me do it by myself first. 3x to the third power plus 4x to the third squared minus 3x plus 7. We're gonna divide it by x plus 2. Yeah, let me do this. That wouldn't take us that much time. At the beginning, I would say something like this. I would say x squared. So for this case, what we would get is, okay, so how about this, 3x squared. In this case, we would get 3x to the third power plus 6x squared. Then what we got would be the 3x to the third power was cancelled out. 4x squared minus 6 squared x would be equal to negative 2 squared x minus 3x plus 7. Oh, I'm pretty sure you couldn't say that. Okay, but now, what could we do? So I'm going to minus 2x. Why I choose a negative 2x? Well, because this one just it's a negative number. So for this case, if we times the negative 2x with x plus 2, what would we get? We would get negative 2x squared minus 4x. So we write it in here. Alright, for this case, the negative 2x squared was cancelled out. Negative 3x plus 4x would be just equal to 1x, which is x. So in the end, we got something like this, x plus 7. For now, I'm pretty sure what I want to do, I just want to plus 1. In that case, we would just minus x minus x plus 2. Okay, for now, the x was cancelled out. Then the 7 minus 2 would be just equal to 5. So in the end, I'm pretty sure what you want to say. I just want to give you the final results, which is 3x squared minus 2x plus 1 and plus 5 over the x plus 2. This is the final answer that I think was it was correct. So I'm gonna take a picture and make it at the, let's say, at the top, so that we could easily say if we got it right later.
Like always, pause this video and try to do it on your own before we work through it together. All right, now let's work through it together. It's into 3x squared.
Yeah, I don't want
3x
to work
squared
through
times
it
2
together.
is 6x squared.
I just want to get
Negative
the final
3.
answer as quickly as possible. Alright, so finally, the solution headed is just like what I did right in here. So we somehow mastered the long division technique or strategy, whatever you call it. Finally, there has a theorem.
Polynomial remainder theorem.
Polynomial remainder theorem. What is that? I have no idea about it. So let's get into it.
Let's introduce ourselves to the polynomial remainder theorem. And as we'll see, it'll feel a little magical at first, but in future videos we will prove it, and we'll see, well, like many things in mathematics, when you actually think it through, maybe it's not so much magic. So what is the polynomial remainder theorem? Well, it tells us that if we start with some polynomial, f of x, so this right over here is a polynomial, and we divide by x minus a, then the remainder from that essentially polynomial long division is going to be f of a. It is going to be f of a. I know this might seem a little bit abstract right now. I'm talking about f of x's and x minus a's. Let's make it a little bit more concrete. So let's say that f of x is equal to, I'm just going to make up let's say a second degree polynomial. This would be true for any polynomial though. So 3x squared minus 4x plus 7. And let's say that a is, I don't know, a is 1. So we're going to divide by x minus 1. So a in this case is equal to 1. So let's just do the polynomial long division. And I encourage you to pause the video, and if you're not unfamiliar with polynomial long division, I encourage you to watch that before watching this video, because I will assume you know how to do polynomial long division. So divide 3x squared minus 4x plus 7 divided by x minus 1. See what you get as your remainder, and see if that remainder really is f of 1. Assuming you've had a go at it. So let's work through it together. So let's divide x minus 1 into 3x squared minus 4x plus 7. All right, a little bit of polynomial long division is never a bad way to start your morning. It's morning for me. I don't know when it is for you. All right, so I always look at the x term here, the highest degree term, and then I'll start with the highest degree term here. So how many times does x go into 3x squared? Well, it goes 3x times. 3x times x is 3x squared. So I'll write 3x over here. I'm writing it in I guess you could say the first degree place. 3x times x is 3x squared. 3x times negative 1 is negative 3x. And now we want to subtract this thing. And this is just the way that you do traditional long division. And so what do we get? Well, 3x squared minus 3x squared, that's just going to be 0. So these just add up to 0. And this negative 4x, this is going to be plus 3x, right? A negative of a negative. Negative 4x plus 3x is going to be negative x. Let me do this in a new color. So it's going to be negative x. And then we can bring down the 7. Complete analogy to how you first learned long division in maybe, I don't know, 3rd or 4th grade. So all I did is I multiplied 3x times this, you get 3x squared minus 3x, and then I subtracted that from 3x squared minus 4x to get this right over here. Or you could say I subtracted it from the whole polynomial, and then I got negative x plus.
Yeah, I don't know the meaning of this video, but let me do a jump.
1 should be equal to 6. It should be equal to this remainder. Now let's verify that. This is going to be equal to 3 times 1 squared, which is going to be 3, minus 4 times 1, so that's just going to be minus 4, plus 7. 3 minus 4 is negative 1, plus 7 is indeed, we deserve a minor drum roll, is indeed equal to 6.
Oh, so what he did here is to assume a formula, or let's say an expression, or here he used a terminology called polynomial. He assumed a polynomial as a function. It has an input of x. If you set the x to 1, the result you get is the remainder that you got when you're doing the long division. Then what's the meaning of that? Why I need to know that? I don't know.
So this is just kind of, at least for this particular case, we're saying, okay, it seems like the polynomial remainder theorem worked, but the utility of it is if someone said, hey, what's the remainder if I were to divide 3x squared minus 4x plus 7 by x minus 1? If all they care about is the remainder, they don't care about the actual quotient, all they care about is the remainder, you can say, hey, look, I can just take that, in this case, a is 1, I can throw that in, I can evaluate f of 1, and I'm going to get 6. I don't have to do all of this business. All I would have to do is this to figure out the remainder of 3x squared, when you take 3x squared minus 4x plus 7 and divide by x minus 1.
Oh, that's amazing. So if someone asks you what's the remainder of this polynomial or equation, or to be specific, this is nothing but okay, if you look at this expression, it's nothing but a number, but it is a number that you couldn't say it is undefined. It's just a number in a range, okay? But in the end, if you know the x, you will get a number. And for every number, for example 4 or 5 or 3 in the programming world, there has an operator called this. I don't know how to use English to express it, but if you use this operator followed by another number, you will always get a result. For example, for this one, 4 with this operator and 2, what you get would be 0. And the 0 here is obviously the remainder. Okay, let me do a search about that. I was curious about it. To remember the meaning of this operator, the first thing we need to do is to know how to read it, how to read this operator.
The percent operator returns the remainder of two numbers.
Okay, the percent operator returns the remainder of two numbers. Yes, I said this is the meaning of that. It returns the remainders of two numbers. Which is just something like this, in the end you get the remainder. Oh, let's say there we got more theorem right in here. For example, how to find the coefficients. Typically I don't know that, but let me just watch this video.
So for what value of c, or values of c, is x minus 5 is x minus, let me write it this way. For what c is x minus 5 a factor of p of x? And I encourage you to pause the video and try to work through it. And that's p is actually a lowercase p of x. All right, so I'm assuming you have attempted this. Now we just have to realize, okay, if x minus 5 is a factor of p of x, that means you could write p of x. Let me do this in that green color. That means you could write p of x as being equal to x minus 5 times some other business, times some other polynomial. So times some other polynomial. I don't know, let's just call it g of x, maybe. G of x. And this would be, well, it would be a second degree polynomial. And so what would p of 5 have to be? Well, p of 5 would have to be 0. 5 would have to be a root of this polynomial. You see it right over here. If you replace this with a 5, and this is going to be a 5, and this is going to be a 5, and it doesn't matter what g of 5 is, this is going to be 0. So if x minus 5 is a factor, if and only if p of 5 is equal to 0. P of 5 is equal to 0. You could say that 5 is a root of the polynomial p. P of 5 is equal to 0. So let's just set p of 5 equal to 0 and then try to solve for c. All right, so we're going to get 5 to the third power. So this right over here, 5 to the third. So p of 5, let me just write down, p of 5 is equal to 5 to the third is 125 plus 2 times 5 squared. So it's 2 times 25 plus 50 plus c times 5 plus 5c plus 10. That needs to be equal to 0. And let's see if we add.
How the hell he know that the p of 5 is equal to 0? At the first, for every expression or polynomial, in Chinese they call it 多项式. Polynomial in this kind of thing, it can always be able to divide it into this form. And what this form was composed, how it was composed? Well, it's just a bunch of factors of that polynomial. It was composed by a lot of factors. And for this kind of form, it has a feature, which is for each factor, because they are connected by a multiplication symbol. So if every factor is 0, the multiplication for all of them would be also equal to 0. So here what he said, x minus 5, if that is a factor, then let's say if we assume this one equal to 0, then we would get x equal to 5. Then we substitute the original polynomial with, we replace the x with 5, we'll get the 0, which is just what I did here. And in that case, we could be able to calculate out the c, because for this expression, or let's say for this equation, we only got one unknown variable. And if we got one unknown variable, we could solve it by using only one equation.
If we were to add 125 to 50 to 10, we are going to get 175, 185. So we get 185 plus 5c is equal to 0. Subtract subtract 185 from both sides, you get 5c is equal to negative 185, or c is equal to negative 185 over 5, which is going to be, it's negative 185 over 5, which is equal to, let's see, 5 goes into 180, let's see, it goes into, what's 5, let's see, it's going to be 30, 5 times 30 is 150. 5 times 30 is 150, and then we'll have another 35 to go, so it's going to be 37, negative 37. Is that right? 5 times 30 is 150, 5 times 7 is 35, yep, negative 37. And we're done. If this was x to the third plus 2x squared minus 37x plus 10, then x minus 5 would be a factor of this polynomial. So for what value of c, or values of c, 2x squared minus 37x plus 5 times 7 is 35, yep, negative 37. And we're done. If this was x to the third plus 2x squared minus 37x plus 10, then x minus 5 would be a factor of this polynomial.
That was quite interesting, but I think it was based, the video we just watched is based on this video. Well, we didn't check this video before we jump into that video, so there may have some gaps between the two videos. So
we're asked, is the expression x minus 3, is this a factor of this fourth degree polynomial? And you could solve this by doing algebraic long division, by taking all of this business and dividing it by x minus 3 and figuring out if you have a remainder. If you do end up with a remainder, then this is not a factor of this. But if you don't have a remainder, then that means that this divides fully into this right over here without a remainder, which means it is a factor. So if the remainder is equal to 0, the remainder is equal to 0 if and only if it's a factor. It is a factor. And we know a very fast way of calculating the remainder of when you take some polynomial and you divide it by a first degree expression like this. I guess you could say when you divide it by a first degree polynomial like this. The polynomial remainder theorem. The polynomial remainder theorem tells us that if we take some polynomial p of x and we were to divide it by some x minus a, then the remainder is just going to be equal to our polynomial evaluated at a. So let's just see what's a in this case. Well, in this case, our a is positive 3. So let's just evaluate our polynomial at x equals 3. If what we get is equal to 0, that means our remainder is 0, and that means that x minus 3 is a factor. If we get some other remainder, that means, well, we have a non-zero remainder, and this isn't a factor. So let's try it out.
God, I think this is kind of hard to understand, so we'd better just listen to it again.
So we're asked, is the expression x minus 3, is this a factor of this fourth degree polynomial? And you could solve this by doing algebraic long division, by taking all of this business and dividing it by x minus 3 and figuring out if you have a remainder. If you do end up with a remainder, then this is not a factor of this. But if you don't have a remainder, then that means that this divides fully into this right over here without a remainder, which means it is a factor. So if the remainder is equal to 0, the remainder is equal to 0 if and only if it's a factor. It is a factor. And we know a very fast way of calculating the remainder of when you take some polynomial and you divide it by a first degree expression like this. I guess you could say when you divide it by a first degree.
Okay, let's first drop out the other information. Just focus on this one single information. It is said that if the remainder equal to 0, then that let's say that number is a factor of your original expression. For example, for now, if we got an original number, let's say 10, then we use this symbol, the remainder symbol. I just named it, or percent symbol, whatever you say. And if we got a 2, okay, if this whole expression equal to 0, then that means the 2 right in here, it is a factor of 10. And for the same reason, you could replace the 10 with this complex polynomial. Then you replace the 2 with this complex expression. All right, that's they share the same idea. That's the first information that we got. Let's move on.
Polynomial like this. The polynomial remainder theorem. The polynomial remainder theorem tells us that if we take some polynomial p of x and we were to divide it by some x minus a, then the remainder is just going to be equal to our polynomial evaluated at a. So let's just see what's a in this case. Well, in this case, our a is positive 3. So let's just evaluate our
so why there we need to be a.
Polynomial at x equals 3, if what we get is equal to 0, that means our remainder is 0, and that means that x minus 3 is a factor. If we get some other remainder, that means, well, we have a non-zero remainder, and this isn't a factor. So let's try it out. So we're going to have, so I'm just going to do it, I'll do it all in magenta. It might be a little computationally intensive. So it's going to be 2 times 3 to the 4th power. 3 to the 4th, 3 to the 3rd is 81. 81 minus 11. Yeah, this is going to get...
Okay, for this theorem, what it did is, it says that the remainder equal to p of a. And if it's equal to 0, then that means this one is a factor of the following polynomial or expression. The real thing that matters is how can you get a remainder of an arbitrary polynomial expression. How do you do that? That's something that we need to know from the previous video.
So we have a polynomial here, and what I'm curious about is what is the remainder if I were to divide this polynomial by, let's just say, x minus, if I were to divide it, I want the remainder when I divide this polynomial by x minus 2. And you could do this, you could figure this out with algebraic long division, but I'll give you a hint. It is much simpler and much less computationally intensive and takes much less space on your paper if you use the polynomial remainder theorem. And if that's unfamiliar to you, there's other videos that actually cover that. So why don't you have a go at it? All right, so now let's work through this together. The polynomial remainder theorem tells us that the remainder, when I take a polynomial, if I take a polynomial p of x, and if I were to divide it by an x minus a, the remainder of that is just going to be equal to p of a. Is just going to be equal to p of a.
Okay, the question is why it is a, or how the remainder theory was proved. We don't know that, so we are going to go to the first video.
This one.
Alright, so
I always look at the x term here, the highest degree term, and then I'll start with a...
So basically from this video, we have no one thing, which is the polynomial remainder theory. What he said is just, what he did is just tell us how this theorem is. But for example, if it's divided by x minus something, then we use that something right in here. We get the f of something like that. But he didn't tell us how that was found, or how that row was discovered. So we would probably get into the last video to know that.
Let's now do a proof of the polynomial remainder theorem. And just to make the proof a little bit tangible, I'm going to start with the example that we saw in the video that introduced the polynomial remainder theorem. We saw that if you took 3x squared minus 4x plus 7 and you divided by x minus 1, you got 3x minus 1 with a remainder of 6. And when we do polynomial long division, how do we know when we got to our remainder? Well, when we get to an expression that has a lower degree than the thing that is the divisor, the thing that we're dividing into the other thing. And so in this example, we could have rewritten what we just did right over here as our f of x. Let me just write it right over here. So we could have said 3x squared minus 4x plus 7 is equal to x minus 1 times the quotient right over here. Or you could say the quotient times x minus 1. So it's going to be equal to this business. It's going to be equal to 3x minus 1 times the divisor times x minus 1. And then you're still going to, and this isn't going to, when you multiply these two things, you're not going to get exactly this. You still have to add the remainder. So plus the remainder. And actually, let me write the actual remainder down. So plus 6. And the analogy here is exactly the analogy to when you did traditional division. If I were to say, actually, let me just show you the analogy. If I were to say 25 divided by 4, you would say, okay, well, 4 goes into 25 6 times. 6 times 4 is 24. You would subtract, and then you would get a remainder. 1. Or another way of saying this is you could say that 25 is equal to 6 times 4 is equal to 6 times 4 plus 1. And so we just did the exact same thing here, but we just did it with expressions. And so once again, I haven't started the proof yet. I just wanted to make you feel comfortable with what I just wrote right over here. If I divided this expression into this polynomial, and I were to get this quotient, that's the same thing as saying this polynomial could be equal to 3x minus 1 times x minus 1 plus 6. Now this is true in general. Let's abstract a little bit. This is our f of x. So that is f of x. So that is f of x. So f of x is going to be equal to whatever the quotient is, and let me call that q of x. So just in a different color. So I'm going to call that q of x. Q of x. This right over here is q of x. So f of x is going to be equal to the quotient q of x times, this is our x minus a. It's, in this case, a is 1, but I'm just trying to generalize it a little bit. So x minus a, and then plus the remainder. Plus the remainder. And we know that the remainder is going to be a constant because the remainder is going to have a lower degree than x minus a, and x minus a is first degree. So this, in order to have a lower degree, this has to be 0th degree. This has to be a constant. So this is true in general. This is true for any polynomial f of x divided by any x minus a. So this is just true. So this is true for any f of x and x minus a. Now, what is going to happen if we evaluate f of a? Well, if f of x is indeed can be written like this, well, we could write f of, let me do a in a new color so it sticks out. We could write f of a would be equal to q of a. So q of a times, I think you might see where this is going, times a minus a plus r. Well, what's that going to be equal to?
Okay, now I got the idea. So basically, why it has to be a? Well, if you write this formula down, if you write this equation, and if you replace the x with a, you would generally notice if the x is indeed a, then a minus a would be 0. So no matter what g of a is, it will always be 0 because it's multiplied by 0. Then in the end, what we left there is the remainder. So that's why it has to be a. Okay, so that's basically today's learning, and in today's learning we have learned about the polynomial division, which is quite useful, as I think, if you have to solve some complex let's say numerator and denominator stuff. But in English, let's say I read it. Oh yeah, if you want to work with some complex fraction polynomial, then you're gonna use this polynomial division. Okay, so that's today's learning, and I'll see you guys in the next one. Bye.